Welcome to today's webinar. The topic today is analysis of air-supported hull in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the German and English webinars, the technical content of the website, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Niklas Wanke. My colleague Clemens Gutmann will be the presenter. He is responsible for the add-on form finding as well as the program RWind, and he works also in the customer support team. Niklas Wanke works also in the customer support team, and he's responsible for the development of the add-on steel design. Okay, I say something how you can ask questions, at least for the attendees who participate the first time. First, switch off my webcam that you can see the full screen. If you have a question, just press the button with the question mark, enter your question in that field, press send, and we will receive your question and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Clemens. Clemens, it's your turn.
Yeah, thank you, Andreas, for the introductory words. I also want to welcome you to today's webinar. Today we are looking at a air-supported hull structure and talking about three main chapters today. First, I'm going to talk about the modeling. Second, how to define the construction stages, as well as the loading, especially our form finding loads. And then in the last chapter, we are looking at the structural analysis results. And I'm going to talk a little bit about possible design ways. So let's jump right in to the program. We are going to create a new file. I'm going to name it air supported, no, that's not correct, supported hull. And today we are using all of the main objects as well as the construction stage analysis and the form finding add-on. And for the design later, I want to use the stress strain analysis. The standards are fine. I'm deactivating the member representatives as I don't need them today. And we can begin by defining our materials. First of all, our membrane material is going to be a PVC membrane type 2. Then we need for the air, dry air as gas. And last but not least, cable, using the Fatse cables today. Okay. Then we need a cross-section for the cable members. And since we get that once in a while in the support channel, we have our according cables that come, for example, this is the material that I picked. So I have several, manufacturer cable diameters, but maybe I want to use a different want to use a different diameter, or have another manufacturer that is not inside our database. So you can do that by using the parametric option round bar. But here you have to consider something. Since the cable is made out of several strands, and between the strands there are holes, you have to consider this, and this is called the filling factor. So you can do that by, in my case, the filling factor is 75%. And since the diameter is with a power of 2 inside of the calculation of the area, you have to draw the root here and multiply that with the original diameter, from the cable. And since the formula expects here meter, I'm going to specify that I'm I want to, this 10 is a millimeter unit. And then you can see that result of the equivalent area, like the actual area that is pure metal without any holes, is 8.7 millimeters. And yeah, like this, you can create your own cable with the diameter that you like. And we need a thickness for our membrane material. And since the material that we're using is of type fabric, the thickness is automatically set to 1 millimeter, as we are not using a stress-based approach, but rather a force-based approach inside the membrane design. And I'm going to explain to you later where this is interesting. Okay, then we can start with our modeling process. I don't want to model a full-sized air-supported hull today, as this takes a little bit longer to calculate. It's not that long, but yeah, it's a difference if the calculation time is 30 seconds versus 2 minutes or something like that. So my hull is going to have membrane 10 meters in width and 6 meters in the other direction. Then we have I want to place cable members on top of that membrane, and to achieve that, the membrane has to be flat. I also could create some geometry in a CAD program and import that as a DXF file or something like that into the program, but I want to do everything today in RFEM 6. So to be able to model this, the surface has to be flat, and then I have the issue that I need to create the volume for the gas, and since the gas cannot be between two surfaces that have zero distance between one another, I have to extrude this a little bit, let's say, into the soil by a little value, and I'm doing that by extruding the surface into a solid, and I'm giving that solid a thickness of 5 centimeters. Then I'm using dry air as a material, and then I'm not creating the surface of type without thickness, as I want to use different stiffness types for the boundary surfaces. Okay, that looks good. We then have to change the solid type, not standard but gas, since we're using a gas, and then we have to assign the initial conditions of that gas, and I want to use the atmospheric pressure, which is 1 bar, as well as 23 degrees as a starting point. Further, I want to use these boundary surfaces with the stiffness type rigid and assign some support to it, rigid support. So yeah, you have like a bowl that is made out of rigid surfaces, and then you have on top the membrane surface. I'm going to deactivate the surface supports, and next would be the definition of the cable members. So let's define them, and I'm using the continuous simple function here, as I want to draw several intermediate nodes, and of course the member type will be of type cable. The rest is okay, and then I'm drawing in a 45. Oh, sorry, made a mistake. Okay, 45-degree angle. Here, those cables. And I'm setting those intermediate points as I want the members to properly connect when creating the grid structure. Because in reality, you'd also have like a connection element between the cables that, to prevent during the inflating process on the construction site, that the cables dislocate from their proper location. Almost done. All right. Then let's select those cables and deselect the surface. I have to deselect the volume as well. Okay. Then I'm going to mirror that about the YZ axis, create copy. And since our hall is 10 meters long, the middle is 5 meters. Okay, that looks good. So that's basically the modeling part. Now on to the construction stages and the loading. I'm going to create several construction stages. First, the form finding number 1. And then a second form finding, number 2. Because I want to use a staged form finding today, I want to do 2 steps within my form finding process. And with the construction stages add-on, I'm able to do that. And then we are having a third one that is going just for the design and the combinatorics later. So in the first construction stage, I want to consider all the members as well as all the surfaces. The solids I'm going to activate later in the form finding number 2 construction stage, as I first want to create the shape of the membrane and the cables, and then activate the gas volume and create the inner overpressure for the final form finding. All right. Then we need according load cases. So my first load case will be also form finding 1. And it's going to contain all the loads that are used in the construction stage form finding 1, and accordingly the load case number 2. Forgot to deactivate the self weight. And then I'm creating some other loads, for example, snow load and a wind load. All right. Good. Now we have to assign those load cases to our construction stage. So the construction stage knows what loads are applied during that construction stage. And in the first construction stage, of course, this is the load case number 1. And in case you're wondering, you have several columns here. And one particularly interesting one is the permanent column. And whenever there's a load case with a checked box here in the color permanent, that means that the deformations and inner stresses and so on that are created by that load case are integrated or taken over into the next construction stage. So maybe you have some load case that is only present during a construction stage, but later on not, or just temporarily, and that this you can consider by using this option. Today this is not interesting for me, but I'm using another option as I want to use the form finding to load case in the construction stage number 2. But in the construction stage number 2, I don't want to consider the load cases of the form finding number 1 anymore. That's why I'm setting its status to inactive. And in the design, finally, I want to use these, and yeah, that looks good. Okay, that's that. So now we are all set with the load cases and combinatorics, and we can continue by with creating our form finding loads. Okay, maybe one last thing. Let's create some object selections. So I want member type cable. So this is cables. And then we have surfaces, stiffness type, membrane, and the third one, solid type, gas. All right. So let's take a look at the membrane first. Like that. And we have several options with our form finding loads. So if you select here load type form finding, you have different parameters that you can set. First of all, there are 2 calculation methods. First the standard one, and then the projection one, which is specifically for those cone-shaped membranes. But since we don't have that today, I'm not going to use that. Further, you have different definition types. Force and stress option that is commonly used, but also a geometrical option, the sag. And with the sag, you define a scaling factor in the warp and weft direction, as well as the size of the sag. And I want to have a sag of 2 meters, so it's more a hall for kids than adults. But with a bigger structure, you can of course create a bigger sag then. And then you have, or you can decide what the sag is, like the measurement is related to. So you can use the base, which are the boundary lines of the surface. You can use a coordinate system, whether this is the global coordinate system or a local one or a custom user-defined one. And the last option is to use another surface. So this is maybe for air cushions where you have several layers of foil and you want to use another foil surface as a reference to create a certain distance between 2 foil surfaces. I'm using the base option today as this is fine for me, and then I hit apply. So this should now it's visible. And since I only created a geometrical boundary condition for the form finding solver doesn't know, okay, shall I go up or go down? Because it's like the sag could be in the positive or negative z direction. That's why I'm going to define another surface load, and this is just going to be of type force in the local z direction minus 0.1 kilonewton per square meter, and I'm going to assign this as well to the surface. Okay, so I defined that the surface should go up. And let's calculate this and let's see what happens. Okay, take a look at the deformations, and this doesn't look at all what I wanted. And why is that? So I calculated the load case form finding 1, and the load case number 1 doesn't know about any construction stage or initial state. The construction stage knows that the load case number 1 is assigned to the construction stage number 1, but the other way around, yeah, the load case doesn't know that it belongs to that construction stage. And if we calculate the construction stage instead, we are going to see, yeah, more likely a result that we want. Okay, that's better, but still not good. So let's take a look. So why is that happening? So we defined a form finding load for the membrane, but forgot to assign a form finding load to the cables. So the cables stay put, they deflect a little bit, but yeah, not nearly as far as we wanted. And that's why I'm going to assign a new member load, also of type form finding. And I have the same, or basically the same options for the members than I had for the surfaces. So I have a force option and I have geometrical options. And I want to use, since I already assigned a geometrical form finding boundary condition for the surface, I'm using instead of form finding type force for the members. And I want to have a very small force inside the cables, just that they are under tension. And I'm going to assign those to all cable members. And then let's try again. And now we are getting in the direction where I want to go. So yeah, we have, maybe we can take a look at the cable members, or at the global deformation. So we have around 2 meters, a little bit more, but yeah, it's still close to what I wanted. And yeah, we could proceed with that, but I want to show you another approach, because this approach has some downsides. So for example, I can define the global sag, but I cannot like granularly decide, okay, I want to go maybe this node a little bit up or in the other direction, I don't know. I want a steeper inclination here on this side. This is not possible by doing this rough definition of form finding loads. Furthermore, I have here near the edge, I have curvature that is switching from one direction to the other direction, and I want to avoid that. That's why I'm going to remodel something, some part of the structure for my second approach. And therefore, first of all, I'm going to create some member sets, and I want to use a different approach. I want to assign the geometrical boundary conditions of my form finding now to the cable members, because then I can tell a group of cable members, okay, I want to have this height in this position and another height in the other position. And that gives me a more granular option to assign local my boundary conditions in a more refined way. Okay, so I'm selecting all my members and creating a member set, and whenever you used an option, you can reuse that option quickly by pressing the enter button. You can see that when you go into the context menu. So what I'm going to do is just select all the members and hit enter 2 times. And that way I'm quicker than searching through the context menu levels. Let's quickly check if we didn't miss anything. Yeah, that looks good. And the next step would be to assign the, let's delete first our loads, to assign those individual member loads. And first, let's do this. First, I want to assign the outermost. I cannot assign two form finding loads to the same member. Okay, I have to use that. Okay, now let's select the outermost ones first and then assign a geometric definition. I want to use the type sag here and use 0.6 meters. And then we can continue to the member set loads. I forgot to activate them. Maybe add them to our definition here. Member sets all. Okay. All right. Member set load, form finding, sag, and then I want to continue with maybe 1.3 meters for the next row. This is this one. All right, I click apply and next. That way I'm staying inside that dialog and have the possibility to assign the next one. So this is that one, as well as that one, and that one. And then the last one. That one. I think I made a mistake. Maybe go one step back. Okay. So 1.7 meters to that one, as well as that one. That one and that one. All right. Now the last ones here in the middle. Okay, good. And again, we need direction for the geometrical boundary conditions, and that's why I'm creating a new surface load, or the old one, and I'm assigning it to surface number 1. And let's try that. Well, that doesn't look, it looks not that bad, but it's the same issue that we had in the beginning with my first approach. So now it's the other way around. We assigned a geometrical load to the cables, but not to the surface. So the membrane deflects in a certain degree, but not as much as we want, because we didn't define that. So I want to create a new surface load and also assign now a force-based form finding definition to it, and maybe, well, let's say 0.1 kilonewton per meters to surface number 1, and then calculate that again, and now it should look good. All right. Yeah, so the shape is different than the first approach, and yeah, you have now all the options to go into detail to create the shape that you want. One thing that I want to address now are the corners. They are still a little bit ugly, and the first thing would be to increase the mesh or decrease the mesh size, as it's quite rough, and try that again. Then using 0.2 meters, run the calculation again. Okay, it's a little bit smoother now, but you can see that it's still, the curvature changes. And to address that, I have to remodel something, some part of the structure. So you can see that the cable members, create cells of that surface. And to be able to have a different loading here in the corner surface cells, I have to divide that surface. And to improve the volume meshing later on, I'm not only going to divide the top surface, but I'm also going to divide the bottom surface. And that's why I'm deleting all the bottom part. Then I divide the surface with all intersecting lines, and then I'm going to extrude these surfaces again into a volume, but now cell-wise. So I want to extrude this into solid, again 0.05 meters with the material dry air, and again I don't want to use the type without thickness. All right, then we have to correct the solid type to gas, and furthermore the stiffness type of the surfaces. First I'm going to select the boundary surfaces. No, let's select all of the surfaces first, and then edit those into without thickness for the inner surfaces, and then for the outer surfaces I want to use again the rigid type. Edit rigid with the support. All right. And now what I want to do as well is to change the local direction of the surfaces. So this will help to correctly apply the loads here in the corners. So what I'm going to do is to go to the wireframe and then select all the inner surfaces, edit And with the option specific axis, you can assign specific axis to the model, and we have a 45-degree angle. You can have different options. You can choose parallel to lines and so on, but this is fine for me. And now you can see that the local surface axes have rotated. Good. So now we can assign more of the form finding loads, or not more, but different ones. So let's go back to the membrane selection, and yeah. So maybe try and take those here and here, and well, let's try 0.3 for the corners. And additionally, I want to have different options, or different ratios for the form finding in those corner surfaces, and that's why I'm going to pick these loads. And now I forgot something. So since the rotation is like all in the same direction, the X and Y axes are different in the different corners. That's why I'm using, so okay, where is the direction? That one. So this is the Y direction, and I want to decrease the factor by like the ratio by a factor of 2. All right, and then the other direction. Headed surface, and now the X component. Good. Let's try that again. Okay. Okay, this might be a little bit strong, so yeah. I'm going to maybe decrease the value a little bit to, I don't know, half of it. So as you can see, this is like, there's no like fundamental best practice to it. So you have several parameters that you play around with, and you have to find the proper setting, and that on the other hand depends on the structure that you have, the loading that you have, the spacing of the cable members, and so on. So I'm giving you just an idea on how to do the general approach, but yeah, I think that looks fine now. Cool. The general approach, and then you have to adapt that, of course, to your project. All right, then let's continue to the second stage. And for the second stage, as I said in the beginning, I want to deactivate all the form finding loads that I had in the first stage, and I want solidly to have a solid load, and that solid load is going to be assigned to all the solids, which are 39. And I want the type gas, and I want a resulting overpressure of 200 Pascal, but yeah, currently the unit is bar. So I go into the options, and the red arrow shows me which is the current unit in the dialog that I'm in, or multiple if there are multiple, changing to that to Pascal, and then 200 Pascal. Okay. And then run the second stage. So now only the inner overpressure, and you can see that the deformation is quite small, only 0.8 millimeters, so it's keeping its shape as the membrane doesn't elongate any longer, and also the cable members do not elongate, they have their final shape, and now only an inner overpressure is applied, and yeah, ensures the integrity of the structure. Then we can proceed to apply the surface loads for the other load cases. I have a snow load case projected in that direction of minus 0.5 assigned to all the surfaces. Apply it next. And for the wind, I'm using the local axis system and apply a load of 1.5 kilonewton per square meter, and again to all surfaces. So this is a very rough approach, at least for the wind. And just one hint, so we have our dedicated program, our wind, that is our CFD, digital CFD canal, and that is especially made for these kind of structures. So whenever you have a structure that isn't covered actually by the standard, the standard doesn't tell you what loads correctly or to apply to that structure. It's very special shape. And this is the perfect situation where our wind comes into place, and again our wind can communicate with RFEM 6. So if you activate the add-on wind simulation here, you can access the capabilities of RWind 3 from RFEM 6. So you define your wind loads, like the tunnel sizes and so on. They are separate webinars where I show this, but I wanted to point out that this would be like a perfect structure to use this digital wind simulation to get more accurate results for these types of structures. Furthermore, we could then analyze what like a standing person on top of the structure would have an impact on the deformation, for example, or if the overpressure leaks somewhere, to have like an emergency. But these are just further ideas. I don't want to elaborate them today. Then I want to show you how to do the combinatorics. So if we go back into the dialog, we created all the construction stages and so on, and now we have for the design, we have to create our design situation. And in this case, I only want to have one, and that is a characteristic design situation. And in order for the combination wizard to know that you want to use the construction stages, you have to tell him that. So, and this can be done by using this option, consider initial state, as a construction stage is also an initial state. And then you have to assign our construction stage number 3 in our case. But for example, if you want to analyze different variants of different form finding approaches and geometries and so on, you can perfectly do that with the construction stage as add-on. So for example, you would then create several initial construction stages, and they don't have to be like in one sequence. So for example, if you go in here, you have a starting one, but you could create a new starting point, and then you have like a whole different branch that you can do totally different things with. So this is very powerful possibility to enhance what you can do within one model file. Okay, but in our case we only have sorry, I have to go here. Initial state, we only want to use the construction stage number 2 for our combinatorics, as I don't want to analyze the happenings during the construction phase. But for example, if you want to, like, you have special load cases, or I don't know what you want to analyze during the erection of the hall, you could do that by creating or by adding other construction stages also as initial state, and the combination wizard will automatically create the combinatorics for you then. All right, that is that. And then let's take a look. And now you can see that the construction stages have automatically been assigned to, like, the previous construction stage is the initial state, and then you have the construction stage that is like the current one as a construction stage, and that one defines which objects are available or used during that load combination calculation. And now I want to deactivate the combination of snow and wind, as I have like no wind pressure but only wind suction, and there are several options to generally influence the combinatorics. The first one is here in the tab Actions, where I have several action types where I can tell, okay, inside one action category I want several or some load cases to combine and some others don't. Please have a look at our online manual for more detail into this. But since I don't want to combine load cases out of different actions, I cannot do that here. And that's why I'm going to the design situation. And here we have this option, consider inclusive, exclusive loads. And that's what I'm going to do. I want to say that whenever the snow load is in a load case, I don't want the in a load combination, sorry, I don't want the load case wind to be present as well. And this goes vice versa. So now I'm only having the form finding and the snow or the wind. And yeah, if you have like more load cases, these of course you can then have a more refined set of what are the inclusive and exclusive load cases. So but you have a powerful tool here to influence the combinatorics and to reduce the number of combinations that are automatically created. All right, I forgot something, as we don't want to calculate actually the results of the load cases, but rather use them as container for our loads. I deactivate those, and then I can go into the calculation of the whole structure. Okay, so here we have this problem with the check all biometrics. So whenever you encounter this issue, you have, like, during the calculation, the mesh gets deformed in such a way that it's like misshaped and the solver cannot continue. So whenever you have this problem, it's a problem with the mesh, and that you have like very large deformations and so on. I don't want to bother you solving this case, so this would be maybe solved by creating here these to have a look at maybe how the mesh can be refined in some point at some point, or maybe the inner overpressure has to be increased or something like that. So in order to be able to continue, I'm going to edit those and just deactivate this load case for now. And of course, like, this is a very sensitive structure, so it's not, yeah, okay, this is still present. And yeah, last but not least, let's take a look at the results of maybe here load case number 4, the wind suction load case, load combination. And yeah, we have several options. You can choose what type of results you want to see. So whenever you have an initial state assigned to a load case or a load combination, you have this option whether you want to see the final results or you want the results minus the results of the initial state. And yeah, this can be, for example, interesting. For example, if you, like with the wind suction, you have the base structure and you want to see what is the deformation solely due to the wind. And in this case, it's 6.8 millimeters. So yeah, this is why the option is present, that you can analyze this. Further, yeah, of course, for the members, we have our normal forces, roughly 5 kilonewtons, and basic stresses, 80 Newton per square millimeter. For the surfaces, we have an option to, like by default, you have the basic stresses on one side, on the other side, and for the principal stresses, for example, also in the middle. But if you check this box, you can see that the items available are reduced, and they are now corresponding to the option, to the setting that you picked here at the top. So for me, I want to use the middle, like the middle of the surfaces, the values, and then inspect the basic stresses in warp and weft direction, for example, here. And yeah, finally, for the volume elements, you can, for example, we wanted to have an overpressure of 200 Pascal, and we can verify that by going into the first combination and activating the solid results for the overpressure, and activate also the gas. There's my results missing. Result objects. Why am I not seeing any results? I see, because there's the wrong initial state. Wait, so this is also the issue maybe here. Okay, so this is the wrong previous state. So I want to use the form finding 2 as a previous state to the design. Okay, so maybe let's calculate all of this again. I have to create the combinatorics, design load cases. All right. Okay. Yeah, now it should work. Calculate all. Yeah, okay, now the error is gone. Okay, apparently previously the gas volume wasn't active at all, and that's why the structure crashed during the second load combination. And now we can take a look at the solid gas, for example, the overpressure, and we set that to 200 Pascal, and that has been reached. Okay. Then I want to briefly show you how to design the cable members, and I'm going to do that by creating a member configuration here. So I want to only use the normal stresses here, and usually cable members are designed by using like a limit force in kilonewtons, for example. But since this is not possible with the add-on stress strain analysis, it's no force analysis add-on, we have to pick user-defined here, and considering all the safety factors and so on, for my cable material, I have roughly around 1000 newtons per square millimeter. And this is assigned to all the members. And then we can configure which elements I want to analyze, and I only want to analyze the cable members. Yeah, and you can see, okay, we have like 80 newtons per square millimeter, which is roughly a design ratio of 8%. So there's room for improvement. But this is not part of today's webinar. So, but just basically, that you know how to perform this. And for the membrane design, I am going back, for example, here to the design situation and take a look at the surface results. And at the beginning, I was telling you about the importance of the thickness of 1 millimeter of membrane surfaces. And this has a reason. So for example, if I turn on the results, so you have like a stress given in Newton per square millimeter, and usually you would expect something like kilonewton per meter, so a force-based result. But this is not possible with a base program, but you have, like, if you know this, it's very easy to continue with the data at hand. So due to the fact that the surface is 1 millimeter thick, and that leads to Newton per square millimeter times millimeter is Newton per millimeter, and Newton per millimeter equals kilonewton per meter. So the value that you have in the display is like 1-to-1 the value that you want, kilonewton per meter. And that's good to know, I think. And so you don't have to recalculate the result that you have here. So with this, according to the code, you have to consider several K factors to consider aging and load history or load duration and so on. So with the results given here in the design situation, or even split up into several design situations where I have snow load and wind load in a separate design situation, I would use those results and go into my custom Excel sheet and perform the design there. Yeah, well, this is everything I wanted to show you. I hope you enjoyed your time and learned something, and I hope my colleagues could answer all your questions. And if not, I'm going to address them later on via email. Thank you for listening, and I'm giving back to Andreas.
Thank you, Clemens, for your nice presentation. Just an additional hint from my side, you can book our online courses for example, for RFEM 6, that's a course for beginners. For the Eurocode 2, reinforced concrete design, Eurocode 3, steel design, and quite new, the Eurocode 5 course for the timber design. And there are also packages with only the Eurocode courses and the Eurocode courses and RFEM 6. For more information, just scan the QR codes, or you can click at the button on the bottom here for more information, prices, and so on. You can download the slides from the same website where you can find the recording and model. On the next days, you will get an email with a link to that page. Okay, that's also all from my side. I thank you for your attention. Thanks to Clemens for the presentation. Thanks to Niklas Wanke for your help by answering the questions. I wish you all a nice rest of the day. Bye-bye.